Hello students, this is the last presentation of transition elements, and in this presentation we will know about how these transition elements form the complexes. If you see most of the transition elements in the form of cations, they have greater tendency to form complexes with the molecules or ions called ligands. Generally, ligands are the ions or the molecules which have ability to donate a pair of electrons to any acceptor. If you see the tendency of formation of complexes, this is due to the cations, which are generally small in size and will have high nuclear charge. This high nuclear charge makes the acceptance of electrons from other molecules or ions called ligands. Then why this transition metals accepts electrons from the ligands? This is due to the presence of vacant inner d orbitals which of appropriate energy, which makes them to accept the lone pair of electrons from the ligands. Due to small size and high nuclear charge and the vacant inner d orbitals of appropriate energy makes the cations of transition metals to accept electrons and forms a complex or forms a coordinate covalent bond. As we told, the bonds in these complexes is nothing but a coordinate covalent bond. A coordinate covalent bond is a special type of a bond where only one atom will be involved in the formation of bond, nothing but only one atom is involved in the donating of a pair of electrons which are required for the formation of bond. Here ligand will donate a pair of electrons and metal simply, that is our transition metal, accepts these electrons. Now see here, this is the pictorial representation of formation of a complex of our transition metal cation. Now here L is nothing but the ligand. This is having a lone pair of electron in its orbital, and here see this is our metal which is having a vacant d orbital. Then what happens? This lone pair of electrons of ligand will be donated into the empty orbital of the metal and forms a coordinate covalent bond, and these electrons will be shared by both metal and ligand. See here, now here this is a metal, and if you take any ligand which is having a nitrogen atom, this pair of electrons will be donated to the metal, and since these electrons are donated from nitrogen to the metal, the direction of the bond it is showed towards the metal. And here if you take any ligand which is having two nitrogen atoms, and then these two pair of electrons are involved in the donation to the metal, then here also they have shown how the electrons are donated into this direction or vacant orbitals of the metal. Now you can also have not only nitrogen, you can of oxygen and sulfur, which also have a lone pair of electrons which are readily involved in donation into the vacant orbitals of the metal. For example, if you take weak ligands like CO, carbon monoxide, nitric oxide, they form complexes only when the transition metals are in a zero or a low oxidation state. Since these ligands will have a donor atom with a vacant orbital in addition with the lone pair. Okay, generally if you take any transition elements, they in order to form a bond with carbon monoxide or nitric oxide, that is NO, then generally our transition metal should be in a low oxidation state. Why? First, this CO or NO will be donating a pair of electrons to our metals. Later on, these weak ligands will accept the filled inner d orbitals through back bonding. Generally, weak ligands, they will form a normal sigma covalent bond where ligands will be donating electrons to the metals and form a sigma covalent bond. Then again what happens? The vacant orbitals of the ligand will accept the electrons from the filled d orbitals of the metal to form a pi bond. Generally, we will call it as a d pi p pi overlap, which will be adding extra strength to our sigma bond. These are the highly electronegative ligands, like even fluoride, chloride will also forms metal complexes. Even these particular ligands forms the complexes with metals present in higher oxidation state. Why? This is because small and highly charged or neutral ligands with a lone pair of electrons forms strong sigma bond by donating a pair of electrons to the metal. And the complexes which are formed by this fluoride or chloride, these complexes have an independent existence. Okay, these complexes have an independent existence. For example, if we are seeing the cobalt present in +3 oxidation state and cobalt in +2 oxidation state, which will form more stable complex. Cobalt 3 will form a more stable complex with ammonia than cobalt 2. Why? If you see the highly electronegative and basic ligand ammonia, they form a strong bonding with cobalt +3 than cobalt 2. This is due to the greater attraction of metal for the ligand electrons, since cobalt in +3 oxidation state is present in higher oxidation state than cobalt 2. Next, trends for complex formation. If you take in each series, that is a 3D, 4D and 5D, each series the stability of the complex increases with increase in the atomic number of the elements. Transition metal atoms, as we know, they will be showing more than one oxidation state, that is a variable oxidation state, and generally higher oxidation state ions forms a more stable complex when compared with that of transition metal atom in the low oxidation state. And if you see the stability of a complex, generally the stability of a complex increases with increase in the strength of the Lewis base. Not only with increase in the oxidation state, even the strength of the complex, nothing but stability of the complex will increases with increase in the strength of the Lewis base, that is our ligand. Poor Lewis bases forms stable complexes due to pi bonding. Pi bonding is a back bonding. Multidentate ligands forms a more stable complex than monodentate. Multidentate ligands. These are the ligands which will be having more than one donor atom. Monodentate means only one donor atoms. Multidentate ligands will form more bondings with the metal, whereas monodentate forms only one bond. More bonds, more stability for that particular complex.